Hello, this is Miss Byron, and today I am going to teach you how to draw Lewis structures for polyatomic ions. So there are a couple different considerations that we need to make when we're drawing polyatomic ions in Lewis structures. So the first, here's our list. The first is going to be brackets. So we have to include brackets and a charge on the outside. So I included a couple examples. You guys were doing this earlier when we did the ionic compound bonding. So you can see that we used to put these in brackets and we put the charge right there on the outside. Same thing needs to happen when we're doing molecular compounds as well. So here's your bracket, here's your closing bracket, and then there's the charge of the overall ion on the outside. Same thing here with the acetate ion. C2H3O2 minus. Ta-da! There's your brackets and there's your charge. I've already showed you guys how to do regular Lewis structures using dots and X's to show ownership of electrons. So what we're going to do that's kind of special on this one is, because like 99% of polyatomic ions are negative, what we're going to do is we are going to show extra electrons as Z's. So it could be any symbol, but I just picked Z's as added electrons. So what I'm going to do for you first is I'm going to do an example. And the example I'm going to show you is O2. O minus 2. And then also, this is going to be like our end problem. Draw all three resonance structures of the carbonate ion. So that is our goal for today. Are you ready? So let's start out really, really easy. And please be super nice to me, mostly because I'm using a stylus and it's like the hardest thing to do Lewis structures for ever. So the simple example that I'm going to show you is O with a -2 charge. So what I'm going to do first is I'm going to draw the 6 valence electrons that it has. And this is just to kind of give you an idea, oh, that's a terrible electron, of what these things look like. So when I add 2 electrons, I'm going to look for the space that needs to be filled to make the octet. And those 2 spots are right there and right there. So what I'm going to do is I'm going to go into those spots and I'm going to put a Z there. And questions that usually come up involve like, hey, where did those electrons come from? Somewhere. Somebody's looking to lose electrons. Somebody must also be looking to gain electrons. So there's my brackets, and then I put my charge on the outside, and again, it can be 2 minus or -2. It doesn't really matter. So to recap here, what I've done is I have shown the number of valence electrons, showed ownership of those by the dots. This says I need to add 2 more electrons. Really, I can add them anywhere I want, so I added them there and there to the empty spots. And then I ended my structure by showing the brackets and then the charge on the outside. So that's a pretty straightforward example. So let's see if we can try a more complicated example. So off to the side, what I'm going to do is I am going to draw the Lewis structures of the elements all by themselves. So nitrogen has 1, 2, 3, 4, 5 valence electrons, 2 on the top, and then 3 separate. And oxygen itself has 1, 2, 3, 4, 5, 6 valence electrons. So nitrogen itself can make 3 bonds. It can make a bond here and a here and here. And in order to do that, that's how it'll get its octet. Oxygen, however, needs to make 2 bonds. It needs to gain 2 electrons from somewhere. The charge on this ion tells me I only have 1 extra electron to play with, so I'm going to save that until the very end so that I can kind of like plug in where I need to. So I know that my nitrogen atom is going to be central. So what I'm going to do first, it's pretty straightforward to give oxygen itself a double bond. So I'm going to give it a double bond. Oxygen is a major player for double bonds. There we go. So now I've got 2 of nitrogen's own electrons, and then it's sharing 2 of oxygen's. Oxygen is happy, nitrogen is deficient. So the other thing that I'm going to do is I am going to take one of these electrons. So my double bond occurred there. I'm going to take this electron and I'm going to shift it up right there, because I am allowed to coordinate covalent bond oxygen, which won't overload my nitrogen, which is going to be kind of nice. So I'm going to go like that, and then I'll put the X's around my oxygen. There's my coordinate covalent bond. So far, nitrogen still needs to gain one electron. And if you look, I've still got that electron right there that I can single bond oxygen to. And I know you're thinking, OMG, I can never single bond oxygen. But wait, oxygen has 2 empty spots, which means that one of the electrons from nitrogen can plug in right there, and then the other one can be occupied by Z, our magic Z. Remember, that's kind of like our ace up the sleeve, if you know what I'm saying. All right, so what I'm going to do is I am going to write, so nitrogen has 1, 2, 3, 4. There's its 5th electron. I'm going to single bond my oxygen. Doot, 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 doot. Oxygen has 6 of its own, and then I'm going to throw the Z in there as well. And so what that accomplishes for me is that this oxygen now has 1, 2, 3, 4, 5, 6 of its own, picks up a 7th from the nitrogen, and then the 8th right there. So what I need to do is I need to rearrange this molecule so that it looks like it does in 3-dimensional space. So right now I've got 1, 2, 3 bonded atoms to my central atom, and I have no lone pairs right here. So in order to maximize repulsion, what's going to happen to this structure is that it is going to spread out in 3-dimensional space to a bond angle of 120 degrees. So over here, I'll draw it over here, I'll have an N double bond O, and I know I'm switching to structural formula, but it's a lot easier with the stylus. Then I also have a single bond oxygen that has 1, 2, 3, 4, 5, and then a Z. And then this other one is a coordinate covalent bond where nitrogen's electrons are being shared to oxygen. 1, 2, 3, 4, 5, 6. And then the last thing that I need around this molecule is I need brackets and a charge. So what I'm going to do is I'm going to kind of like shrink this and put it off to the side. This actually has resonance structures. So there are multiple ways that I can draw this molecule. So if you watch, oh, hello. So if you watch, I'm going to shrink this off to the side. There you go. And I'm going to redraw, I'll use a different color too. I'll redraw this molecule with all of its resonance structures. So to indicate resonance, what we're going to do is we're going to show a double-headed arrow, and then we're going to draw our structures right in a line. So this is one legit structure, so I'm kind of okay with that. The next one, I'll start my brackets, and let's pretend the single bond was up top. 3, 4, pretend there's a Z in there. There it is, see it? Okay. Then I'll double bond this O. Doot, 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 doot. And then I'm going to coordinate covalent this friend. Here's my O. 1, 2, 3, 4, 5, 6. Close it out. Minus another resonance structure. So now what I've done is I'm moving the bond. I'm not moving the atoms. So if you look here, the double bond is on the top. Pretend those atoms are staying in place. I could have drawn the double bond here, which is what is shown in this drawing. And then for my last drawing, I'm going to take my double bond and I'm going to move it here. So this molecule, this nitrate ion, actually has 3 resonance structures. So I'm going to put my double here first, just so I don't forget where it needs to go. There's my double. And this one, honestly, these are all single bonds. It doesn't really matter which one you put where. The only difference between a coordinate covalent bond and a single bond is where the electrons came from. In all other circumstances, like in bond length, bond energy, all of those things, they're identical. So it's quite all right. And it's not resonance, actually. It's not resonance if you just move a single and a coordinate covalent. That is not a resonance structure. They're both single bonds, and you're doing shenanigans, so cut it out. All right, so what we've got here is we've got our 3 resonance structures. We've got resonance structure 1, resonance structure 2, resonance structure 3. We have brackets and a charge shown for each ion. We are looking pretty good here. So that is nitrate. And then let's see. The last one to draw as an example is going to be the carbonate ion. So the carbonate ion is CO3 2-, which means we have 2 electrons to try to fit on there. So what I want you to do is I want you to try to draw the carbonate ion with polyatomic ions. Oxygens are notorious for doing single bonds, and that's a really easy place to put that 2- charge. So single bond a couple, see what happens. And I'm going to wait a second, and then we're going to come back. All right? Okay, you try to draw them, and pause the video here. All right. So coming back to this example, what we've got is, let's draw our atoms off to the side first. A carbon with 1, 2, 3, 4 valence electrons, and a couple oxygens with 1, 2, 3, 4, 5, 6 valence electrons. So I can already tell right now, just by looking at this, so carbon can make 4 bonds, 1, 2, 3, 4. It's got 4 empty spots in it. And because I've only got 3 oxygens to play with, I already know that carbon's going to be doing some multiple bonding. What I mean by that is it's going to have more than a single bond. It's going to have a double or a triple somewhere. Now, if I were to use a triple bond, I think I'd be taking up too much room, too many electrons on carbon. So I would be taking up like all of those, and that's kind of a bad sign. So let's do a double first. So I'll do carbon, and I'll do 2 dots on top. X, X. Okay, so there's my double bonded O. Now, I have 2 more oxygens to put onto here, and I do know that I have 2 more electrons on carbon that are remaining. So I know I'm going to have 3 regions of electron density. That means they're going to be spread out to 120 degrees in a trigonal planar. So I'm going to try to draw it that way first this time. So as I said before, when we're looking at polyatomic ions and you look at your charge, you look at your negative charge here, oxygen is a prime candidate for taking those electrons due to its high electronegativity. Also, the fact that it can make 2 bonds means it can single here, and then the extras just plug in the extra spot. So that's exactly what I'm going to do. Let's see. So I'm going to single bond some O's. Wow, that's a terrible O. Okay, and I'll put the Z in extra. Doesn't really matter where you put the Z, just for my own personal preference, I never put them as a bonding electron. So here, let me put the Z in, and then I'll show you where. So I never put the electrons in here, up next to the central atom. I put them on the outside somewhere, because that's usually where they're more likely to jump in. So the last thing that I need here is I need brackets. And the charge on the outside, 2-. Now, if you notice, again, so polyatomics, same thing, very notorious for this. This molecule is going to show resonance, and I can tell that because I have multiple bond types. I've got double right there, and then 2 singles down here. So what I could have done is, instead of drawing the double at the top, I could put the double here. Instead of drawing the double on the top, I could have put the double here. So this has 3 resonance structures that I am going to need to draw. So I put my double-headed arrow just to show, hey, resonance structure. And I'm going to do the structural formula here just to show it a little faster. There's my Z. Doesn't matter where I put this. Z, X, X, and then I'll double down here. And then bracket, bracket, charge, 2-, and Here, let's see if I can move those friends out of the frame. Move him over. move him over, and then I think I've got room for my next friend. So my other resonance structure, I have already put a double on top, and then I put a double around to the right. So I just need one more. I have to show the double bond down here. So I'm going to do my carbon, and I'm going to put my double there first, just so I don't forget where it needs to go. Now the others will be singles. And then Z, here's my oxygen, X, 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 Z. Last thing I need, brackets, and charge on the outside. So always make sure with polyatomic ions that you're paying attention to resonance structures. They are notorious for resonance structures. So to summarize what we've got here, so at the very beginning, we talked about some special considerations that you need to have for polyatomic ions. One is that you need to finish them up with brackets and a charge. That just shows that there are added electrons in the case of most polyatomics. Most are negative. And these electrons just kind of come from the environment. The added electrons themselves we show as a Z. Try to avoid using them as a bonding pair, so don't put them in between atoms. Keep them off to the outside. And I think that's about it. If you're going to show a positive ion, usually what's going to happen is instead of having a hydrogen that's like that, it turns into a hydrogen that has lost an electron. So really, what is it at that point? Just a proton. So these are going to coordinate covalent bond onto the top of something if you have a plus ion. I hope this helps, and I hope this allows you to draw ions more easily. And if you need more help, please ask me in class.